because that takes us on to our topic today, which is historic engineering. And as I said, it's a bit different. We're looking back into history where we can learn a lot. Industry memory can be lost through generations. Personal experience of situations or disasters have a large impact on the culture that person has. But once that personal experience is lost, then the lessons learned become more remote and therefore not necessarily considered in as high regard. So take any disasters, for example, and this one is Barton Bridge in 1959. The temporary work, or the failure that was associated with the poorly planning temporary works killed 2 people and 8 were injured. The scaffold wasn't designed properly. Essentially, it was observed as bowing before, but that was left until it failed, and the thing failed. Lateral torsional buckling kind of failure. Several large-scale disasters associated with poorly planned temporary works during the 50s, the 60s and 70s ultimately led to a report being commissioned by Sir Stephen Bragg, and that was called the Bragg Report. And this report included 27 recommendations, which were predominantly incorporated and adopted into 5975. And that Bragg Report is actually quite a good read, and a lot of the content is relatable to what we do today. Because when people directly involved in such events retire or move to different parts of the industry, then the very intense personal lessons taken from this experience can be lost if it's not recorded or passed on. And that's why it's important to know where you've come from to enable you to know the direction you're going to be moving onto, to better things and onto better improvement. Which is why I thought it'd be a great idea to delve into some historic engineering today. So, historic engineering, where to start? I could go way, way, way back. However, seeing as our case study is based on a full-scale model of a medieval trebuchet and the redevelopment of that, I've skipped quite a few centuries and started in the medieval times. This is a time where much more sophisticated technology was available, and we knew a good bit more about engineering than, say, the Romans, namely because we've had a little bit more practice and experience. So what is medieval engineering? It refers to the technological and architectural practices employed during the Middle Ages, spanning roughly from the 5th to the 15th century in Europe. And this era witnessed significant advancements in engineering techniques, materials and construction methods, which had quite a profound impact on the development of cities, castles, cathedrals and various infrastructure. One of the most remarkable achievements of medieval engineering was the construction of some massive cathedrals and churches. Gothic architecture, which emerged during the 12th century, revolutionized the design and construction of these structures, and Gothic cathedrals featured pointy arches, ribbed vaults, flying buttresses, and large stained glass windows. And these architectural innovations allowed for taller and more spacious interiors, while distributing the weight of the structures more efficiently. And notable examples of these structures, the Notre Dame in Paris and loads of others in French cathedrals, but there's some really great British examples as well, such as Salisbury Cathedral, which you can see in the middle there, and Canterbury Cathedral on the left. So there's lots of arches, all acting in compression. And that Gothic engineering used some basic engineering principles that we still use today. Take this example on the right that I've taken there. That shows how the arch supports are kept stable by adding a stabilizing weight to the top to resist that horizontal thrust that you get from the springing point of an arch. And I've got a couple of examples where this exact same engineering principle was used in a bridge redevelopment project we worked on in North London. So we've got an excavator operating on a footpath that's riddled with services. And if we take a section through here where I've put those arrows, we can see what's going on. And there's no need to put mats down directly on the footpath to lower the ground bearing pressure to make sure we're not affecting the services. We can just totally span over it. And also, while we're doing that, we're stabilizing the retaining wall as it's loading using the same principle that we had in that Gothic architecture. Got another example. So similarly, when we're using a mobile crane to lift in the services bridge adjacent to the span, We use a crane that's got outriggers that lines up with the abutments, which is quite fortuitous. That was the crane that suited the loadings in this particular project. And these outrigger loadings then stabilize the abutments, increasing the stability and therefore the overall safety. The original idea shown in that part 2 there at the bottom right was really, well, it successfully identified the risk associated with loading the bridge or putting a surcharge on those abutments, but it required a larger crane because we had to sit it further away. And if we look at those implications here, we're still loading the bridge abutment from surcharge loadings. It took longer to use with rigging and de-rigging. It cost more to hire because we had a bigger crane. The driver was further away from the action. There's just so many things that were nowhere near as good as using your head and deploying some good engineering. So that option 1 was the preferred solution and what we went with. And by the way, that vertical thrust effect on eccentricity figure is straight from my well-thumbed copy of the J.E. Gordon's book shown here on the right there. Includes some great illustrations and engineering explanations in layman terms, because take that picture on the bottom left. So we've got material science explaining why a short worm has just as much chance against a blackbird as a long worm does. So that stress distribution in materials of relative stiffness explanations like this, and come on, that's pretty astonishing stuff. That's definitely well worth a read. So anyway, back to the agenda. Medieval engineers also focused on fortifications and castle design to ensure security and defence during times of conflict, and castles were strategically positioned and designed to withstand sieges and attacks. Motte and Bailey castles, which initially popular in the early medieval period, consisted of a raised earthwork mound called a motte, and then a wooden tower on top with an enclosed kind of courtyard, which was called a bailey. Then later, we had stone castles that became more prevalent, and with features such as curtain walls, towers, moats, drawbridges. Castles like the Tower of London, Carnarvon, Hedingham, Harlech, Conway, Rochester, just to name a few. Wales have some great castles, and I'm fortunate enough to live in the northwest and hopping into Wales a lot as a child to see these amazing structures. And that's Carnarvon Castle on the left-hand side, and the Eagle Tower, I think, which is a great example of these heavy feats during the early engineering in action. And on the right there, that's Hedingham Castle, which is more of a keep, and that one's very tall and skinny. And you can see the entrance there up the ramp. So the entrance to the castle is much more difficult to get to for those who are laying siege. And that Hedingham Castle is in Essex. A great book on the development of these structures is Castle by Mark Morris, as there's certainly a lot to be said on this subject that I haven't got time to go into today. But I will give you a little historic case study that includes both temporary works, castles, and engineering principles. I know, right? Pretty incredible, but hear me out. So Rochester Castle is in Rochester in Kent, and it's a very advantageous point right on the mouth of the River Medway. This is a short story of why the round tower replaced the original square one, which was demolished by King John when he laid siege to the castle in 1215. And the castle was under general siege at this time, being attacked by King John and his army, bombarded and pestered to high heaven to oust those cheeky rebels that were inside. So the castle is an older keep type structure with the fortified defensive wall around the outside. But you'll notice that one of the turrets on the outside on that wall is now round. And that's because that miners digging beneath the ground and towards the castle undermined the square one, leading to its collapse, which allowed King's forces to breach the defences. And the miners would have had to have used, yes, you've guessed it, temporary works to support the underground tunnel and prevent it collapsing prematurely. They would have also underpinned the square tower with timber struts, then laid firewood, hay and straw in the tunnel all along their way out as they move out. And then this was set alight, thus collapsing the struts and removing the support of the wall. That's essentially the opposite of what we're trying to do when we do underpinning, i.e. keep the building more stable, but it's the same principle. So that round tower, of course, is not so easily undermined as it has a lot more even load distribution. And this principle is seen when we look at castles that were built across the ages and compare them. So you can see here, we've got a couple of snaps from a great book that I've got on lots of different castle plans. And you can see that Middleham Castle having rather pointy corners on the left. So that's typical for an early keep type structure. And then more than 100 years later, we got Warwick Castle, which is still that same keep type structure. But this one has rounded corners, much better to defend against those pesky miners. This is engineering technological advances in action. So that's castles. What else is there? There's water management, which was another crucial aspect of medieval engineering. Engineers developed sophisticated systems for irrigation, drainage, and water supply. They constructed aqueducts, canals, and reservoirs to transport and store water for agricultural purposes and urban settlements. And the remarkable Roman aqueducts, such as the Pont de Gard, were also repaired and maintained during this medieval period. And it was during the Middle Ages that the bridge was adapted to the passage of men and beasts. I just thought when I read that, imagine the description of that on a modern client briefing. But a path was built and columns on the second level were cut away over half of their thickness, threatening the stability of that structure. So have we got an early cut and carve demolition kind of scenario here? And it seems like a good opportunity to mention that we've got a cut and carve webinar on our YouTube channel, which is especially about cutting structures into big holy structures akin to Swiss cheese, and perhaps not ancient viaducts, but like we've just seen. But all the same, we're looking at load paths, load history phenomena, sequencing of demolition. It's really important to make sure we maintain the stability of structures, and engineers would have had to have understood the structure to carry out that work, or perhaps been a little bit lucky. But I think that they were smart enough and knew how they could understand those basic engineering principles to make these structures stand for such a long time. We've also got transportation and infrastructure. They also saw notable advancements during this rough time between the 5th to the 15th century in Europe. We've got roads and bridges were constructed to facilitate trade and travel. Roman road network was expanded and improved upon, allowing more efficient and safer passage, and stone bridges were built featuring arches that provided stability and durability. One famous example is the medieval bridge in Avignon, France, called the Pont d'Avignon. It enabled one of the most important pilgrimage routes between Italy and Spain, and some of the foundations for this bridge appear to have been built by the Romans, where an earlier river crossing was. So it's quite a popular crossing of the river there. Another example of what did the Romans ever do for us? Unfortunately, the arches of this bridge had a nasty tendency to collapse every time the river flooded, which was quite expensive to repair. So as it was very difficult to maintain this bridge, when it collapsed in the mid-17th century, it was abandoned. But the surviving arches are still there today, as shown. So in terms of technical innovation, medieval engineers developed mechanical devices and machinery to aid in various tasks. Water mills were widely used for grinding grain, sawing wood, and various industrial processes. Windmills also emerged during this period. Mechanical clocks even, which there's an example of an astronomical clock in Prague. These were invented to measure time much more accurately. And this is a fantastic illustration that I found of a crane powered by a treadmill. Ingenuity of using alternative uses of power to speed up construction time. And in this instance, peasant power, which I thought was quite interesting. And I also think I've spotted the engineer that might be responsible for the design. I can't look. I thought that was great. So while medieval engineering lacked the scientific knowledge and advanced tools of later periods, it demonstrated remarkable ingenuity and craftsmanship. The architectural and engineering achievements of the Middle Ages continue to inspire and awe people to this day, showcasing some remarkable skills and creativity of medieval engineers. A few examples I've shown here. So medieval engineering is a very interesting topic, but of course, engineering goes much further back than the medieval, and as engineering is synonymous with temporary works, then boy, you've got it. Temporary works has also been going on for centuries. The Romans had catapults, and so did the ancient Greeks. And that's without touching on the engineering and, of course, the temporary works associated with building the ancient pyramids of Giza. So, folks, temporary works we see today are but the pinnacle of centuries of engineering experience and knowledge. And that is, in a brief overview, how we get from the historic engineering of the pyramids of Giza through Gothic structures such as the Tower of Pisa, and that's Pyramids Giza, Leaning Tower Pisa, to temporary works. And after that awfully crowbarring joke, I think I'm going to show you a case study on Warwick Castle. I'm going to share with you the opportunity I had on working on the redevelopment of the king of medieval siege artillery, and that is the counterbalance trebuchet. So this particular trebuchet is at Warwick Castle in Warwickshire in the West Midlands, and there aren't many trebuchets about. I know that Caerphilly Castle have one, but it certainly used to. But the working model that is at Warwick is quite an engineering marvel. Warwick Castle itself is a medieval castle developed from a wooden fort, originally built by William the Conqueror in 1068. And it's passed hands via many various means, and now is with the current owners, which is Merlin Entertainment, who were the client for this job. And the whole place has been redeveloped a great deal since Big William the Conqueror had his wooden fort there. That's for sure. And changing the old trebuchet out for a new one was the latest project at the castle. Carpenter Oak were the contractor carrying out the works, and we assisted in the temporary works that were associated. I'd like to thank Carpenter Oak for sending me their photos as well. But the Carpenter Oak are a very knowledgeable heavy timber frame specialist, and made and constructed the new frame, as well as dismantled and deconstructed the old timber frame, whilst keeping all of the ironwork to be reused. They had a crack team of tree surgeons who effectively were able to make the necessary cuts as part of the dismantling process. And this project was no mean feat. The trebuchet at Warwick is rumoured to be the largest in the world. I'm not sure if that's a humble brag, but it's certainly very, very big. The castle itself is great as well. At Warwick Castle, if you ever get to see it and the ground it's on, it's well worth a visit. And you can see the trebuchet in action there. So these trebuchets are very big structures. Of all the siege machines, the trebuchet is the largest and the most destructive, and the counterweight ballast box used on some of them is said to have been bigger than a peasant's hut in some instances. A nice unit that I'm going to try and squeeze in somewhere in my calculations in the future. Peasant huts, how many peasant hut size? It's used to as a simple fulcrum catapult that would use the lever arms to project a 150 to 300 kilogram weight into the air and at a castle or some large target. The maximum range is around 450 meters or so, and it was more accurate than the alternative siege engines that fired projectiles. It was mainly used for knocking down big walls of castles. And the use of this structure included an engineer who was in charge of using it and would typically load the ammunition ready to be launched and before the pin gets pulled. So the Warwick Castle trebuchet shown here on the left was built in 2005 and was part of a daily show, which we'll see a little bit of a little bit later on. It was 18 meters tall, 22 tons in weight, and had around about 300 individual components. It had 6 tons of box and rubble, which were the counterweight, and that was lifted up and then dropped to wreak destruction on the poor souls located at the receiving end of this giant timber beast. It used the laws of conservation of energy with the compound action from different lever arms to maximize stored energy from that hoisted up ballast box to the projectile being fired once it was released. It's pretty smart, really, for those smelly medieval engineers, I think, because the trebuchet was invented about 500 years before Isaac Newton was around to establish the basic laws of motion. So it's good engineering in practice here, from trial and error, more than likely. The Castle defences were no match for machines like this, and sometimes even just the word of mouth that the siege engine of a trebuchet is coming, that would mean that the siege would end. They'd just give up because they thought, blimey, this thing's coming along, we've got no chance. So at Warwick Castle, the arm is set by using tread wheels that look like giant hamster wheels, and these pull the arm down and then lift the ballast box up, and then the arm is locked off before being loaded up and released with a pin. There are alternatives to setting the arm, which included manpower pulling the arm down, just lots of burly, hairy men pulling the arm down usually, or using animals to and a winch to pull it down. And I have seen the odd tractor as well used, although I suspect that that's more of a contemporary method. There are some illustrations here from my drawing, which identified the temporary bracing required as part of the removal sequence. And there's a little man on the right-hand side there, which I've put in there to give you a sense of scale of how big this thing is. And this is the main temporary works drawing that supplemented the calculation reports that ensured the stability of the structure during the removal sequence, and justification of the timbers used as bracing, which were generally moved around to suit the components that were being removed at that time, and the length of time that it was left in its partially demolished state out of hours. We've got a scaffold design that was also carried out to take the weight of the ballast box so that we could remove the main throwing arm that it was slung to. And then the ground was quite soft in this area, and so we used the base frame of the trebuchet in places for a better footing for the scaffold legs. And here's me during some of the removal process. So one of the heaviest lifts that's about to be lifted there is the main tread wheel, or the furthest tread wheel away, which came in around 1.2 tons. And because one of the tread wheels was on that far side, that's where the crane was at its maximum reach. And the crane also had to come across a very small bridge as well, which was the only access available to the trebuchet on its little island. We've got some bracing here shown later in the works as the frame starts being removed and it's coming down. You can see that main axle going across there between the two giant tread wheels. And then this is the main A-frame with the arm off and the outrigger legs partially removed with the castle in the background. This is the other giant hamster wheel coming off, and also some pictures of the ironmongery that was salvaged from the structure that were to be reconditioned and reused. It ended up being like a giant puzzle at the end of it. And then this is a view from the top. So we sequenced the works so that the minimum temporary works was required, which ended up being just a few timber braces in places, because it's living to our mantra of no temporary works is the best temporary works. If we can sequence it and use what we have to hand to take the structure's stability mechanisms in the temporary term, then that's what we do. We try to remove as much temporary works as we can. And then now here's the new one being built. So we got 22 tons of timber with the A-frame and the tread wheels made from oak, and then the main throwing arm made of ash. Some great carpentry work that turned out to be quite a really amazing structure. So all credit to Carpenter Oak there. And it's the same design as the older one, with the large base and mechanics which were typical for trebuchet of this type. And the thing was handcrafted in their workshop in Devon and then transported up to site. It was rebuilt earlier this year, ready for the tourist season at Warwick Castle. And here's the new trebuchet in action.
8, 7, 6, 5, 4, 3, 2, 1, loose!
That's the new trebuchet and the entertaining amateur dramatics that the team put on there of the Trebuchet destroying, I think it's a cannon that they're trying to get. But you got to remember that the Trebuchet was the largest and most formidable of the siege engines, and was in essence just a giant catapult you can see swinging around there. It was used to hurl huge projectiles to breach the castle walls, large rocks. I'll just jot this back a bit. Large rocks, all sorts of ammunition, including stuff that's on fire, to hurl it over the walls and to create some destruction. Beehives, fireballs, manure, dead animals, diseased animals were also hurled over to the besieged castle, just to spread general discomfort and destruction. Pigs were often, interestingly, picked as the animal of choice, as they thought that they were a bit more aerodynamic. Make of that of what you will. The testing associated with that choice must have been quite interesting. And of course, everyone knows that that's where the phrase comes from, pigs might fly. I actually made that bit up, but you know, who knows. But I think we can all agree, a very entertaining spectacle there. So we've seen today an overview of historic engineering, and I thought it'd be useful to or just interesting to use the benchmark list that the ICE put together to mark professionally qualified engineers with what I use to when I'm mentoring my engineers at Andun, to have a good comparison. So I thought this would be interesting to review. So if we take number one, I think understanding and application of air engineering is a big tick. We're much further along today than we were. And of course, by medieval times, the engineers had more experience of the utilization at scale of timber. So the size of the machines went up compared to the Romans and those before. And then this only increases with time and experience to where we are today. Other big ticks for me are health and safety, commercial abilities, and also communication has had major advances with modern technology. The last one, professional commitment, I think that's up and down, because although some people would literally lay their lives down for the job, probably not out of choice, I might add, in medieval times, but they may or may not have considered careers as seriously as we do today. However, apprentices for master masons, for example, would have had to have been seriously committed to training. So maybe that one's up for debate. But interesting ones for me are leadership and sustainability. So rightly or wrongly, gone are the days of super industry leaders in civil engineering, such as Telford, Stevenson and Brunel, those kind of leaders who inspire engineers even today and seem to take on engineering feats that were pushing the boundaries of engineering at the time, with one person seemingly responsible for the whole lot, although we know that's not true. But you know, we've got a figurehead who appears to just do everything. And a quick Google on modern engineering industry leaders brought up for me brought up Elon Musk when I had a quick look. But I'm sorry, I just think there's no comparison to those like from Elon Musk to those like Joseph Bazalgette, or the engineer behind underground sewers and the saviour of London and the Big Stink. And the other one is sustainability. So siege machines like the catapults and trebuchets were made from wood found in forests around the castle. Siege towers were built and ladders made from just the resources that were around and on hand, so they didn't have to carry them around everywhere. And the technology being used was simpler and sustainable, using more organic materials. And these were also times where the population was a lot lower and the burden on the planet was much, much lower. So now it's a much different picture, but a picture that I think is changing for the better. And that's all I'm going to kind of say on that subject. And further details on that, we can look at our net zero, construction net zero YouTube video, which we've got on our YouTube channel, for more information on there. And there's a lot of information out there on temporary works. So we've got temporary works forum guidance. There's a website there, lots of free content. We've got 5975 itself, which is the go-to code for temporary works design and procedural control of temporary works. We've got the Safe by Design early focus on constructability in temporary works, and also the Andun webinars and our temporary works flowchart too. We've got, I think, more than 60 videos on there, with lots of content ranging from complex demolition studies the net zero challenges, like I mentioned, to a crash course in plate bearing testing working platforms. And in terms of historical engineering, there's a wealth of literature. A great starting place is YouTube. There's lots of content on there. There's some great TV series as well. There's a really good one made by the French where they really rebuilt a medieval castle in a TV series, and it was an excellent overview of what they did and the trebuchet they had there and an assessment of its construction and performance. There's a series by Jon Snow called Battle Castle. It's another great TV series. There are local interest groups. I know the ICE have a historical engineering group in the Northwest, which is a wealth of knowledge to dip into. And then the books I've mentioned too. We've got that Castle by Mark Morris, J.E. Gordon, Structures or Why Things Don't Fall Down. There's some from my personal library of The Secret Lives of Buildings, which is, oh, you can't see that one, but that one's good. Bruno Leschi's dope.